Hello folks, this is Mike. Welcome back to Foundations of Math 2, coming back at you with another video here. In the previous video, we got an introduction into logic, logical forms, logical connectors, quantifiers, and all that good stuff. In this video, we are going to dive deeper into when logical forms are true or false through the use of truth tables. So, as I said, we want to know all possible cases for when logical forms are true or false. And when I say all possible cases, I mean regardless of the combination of truth values for its components P and Q, or P and Q and R. And the way we do this is with truth tables. So what you do when you set up a truth table, you'll be given your logical form, and you create columns. You create a column for each letter that shows up in there. So if you're just seeing P and Q, you'll have two columns, one for P, one for Q. If you have P, Q, and R, you'll have three columns so far. And then what you do is you create a new column for every piece that is involved in the given logical form. And then your final column should be the column that gives you the truth values of the logical form that you were handed at the beginning. But to fill in the truth table for a general logical form, when we talked about those logical connectors in the previous video, we need to know what those things do to the truth values of simple statements P and or Q. So first off, the negation. From the previous video, we said that the negation simply switches the truth value. So here I have some simple statement, which I've named P. It is either true or false. Then not P, we see that the truth value gets switched. If P was true, not P is false. If P was false, then not P is true. If you just have one letter involved, like just P, you're going to have two rows underneath that. If you have two letters, like we will for the remaining basic connectors here, P and Q, then you're going to have four rows. And those rows will go, the columns, P will go true, true, false, false, and Q will go true, false, true, false. If we have three letters, P, Q, and R, then we're going to have 8 rows underneath that. P, true, 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 false, 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 false. Q will go true, true, false, false, true, true, false, false. And R will go true, false, true, false, true, false, and true, false. So this was the negation. The disjunction. See, we have P and Q, and then, as we just said, 4 rows down here. P goes true, true, false, false. Q goes true, false, true, false. This gives us every possible combination of truth values for P and Q. And the disjunction, as long as one of the two is true, then the disjunction is true. So for P or Q, at least one T in one of these two columns means it's T here. So we have true, 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 and false. Next up is the conjunction. The conjunction, in order for the conjunction to be true, both pieces have to be true at the same time. So again, 4 rows, P, T, T, F, F. Q goes T, F, T, F. And now P and Q are true, which makes the conjunction true. Every other case of these 3 here, at least one is false, which makes the conjunction false. Next up is the conditional. P implies Q. Again, same setup for P and Q, true, true, false, false, true, false, true, false. For the conditional, a true implying a true makes it true. A true implying a false makes the conditional false. A false implying a true makes the conditional true. And a false implying a false makes the conditional true. Now, those last two rows may seem a little bit odd. How can a false implying a true make it true, and how can a false implying a false make it true? Well, just as a couple quick terms here, in the conditional, P implies Q. P is called the hypothesis or hypotheses, and Q is called the conclusion. If we have false hypotheses, we can't say that the conclusion is false. These last two cases here are examples of statements being what is known as vacuously true. Because the hypotheses, because the premise that this is based on is false, we can't say that the conclusion is false for sure, so we have to say that it is true. An example of a vacuously true statement is actually what we saw in the previous video. The statement was, if the sky is green, then pigs are purple. Well, the sky is not green, so vacuously, that sentence, that entire conditional statement is indeed true. So those last two rows there, the ones where we have our red arrows, those are examples or the cases where a statement is vacuously true. And then lastly, the biconditional, P if and only if Q. Again, same setup here for the first two columns. The biconditional is true when P and Q are the same, either both true or both false. When they're not the same truth value, the biconditional is false. So now that we have these basic truth tables down, let's create the truth tables for a general arbitrary logic form. So we're going to create the truth table for P or Q implies not Q. So looking at this logical form right here, first we note that there's only two letters involved, P and Q. Another thing we notice, overall, we're doing an implication here. We have this thing implying this thing here. Now, these things before and after this arrow, we have a disjunction, and then we have a negation here. So let's get our table set up. I have the columns for P and Q because those are the only two letters there. And note that I created a column for each piece in the overall logic form here. I have the P or Q. I have the not Q. And then when I know those two things, I can then determine the conditional involving those two things. So we go column by column, we fill in all of the entries or all the blank spaces in that column. If P is true and Q is true, then the disjunction is going to be true because at least one of them is true. If P is true and Q is false, a true or a false gives me a true. A false or a true does the same thing. It gives me a true. And then lastly, a false or a false gives me a false here. So we've completed that column. We have the truth values for P or Q in every possibility. Next up, the column for not Q. We're simply going to change the truth value of whatever Q is, because that's what the negation does. So here Q is true, which means that will be false. Here Q is false, which means that'll be true. Here Q is true, so that'll be false. And then here Q is false, so that will be true. There's that fourth column. We only have one more column to fill in, and that's the column for the given logical form. So I have this implying this. We're going to see what this turns out to be. I have a true implying a false. Looking back at our table for how the conditional works, a true implying a false means that that's false. Here we have a true implying a true. The conditional truth table says a true implying a true is true. We have another true implying a false, just like the first row. That's going to be false. And then last row we have false implying a true, and that is one of those two instances where the statement is vacuously true. So the final column there goes false, true, false, true. And that's how we create a truth table. This is how we create our columns. Again, we have a column for every single piece, as well as every step leading up to each piece in the overall logical form. And then we have our final column, which is the column that we fill in for that given logical form. Now we're going to do a sample of where we have three letters, P, Q, and R showing up in there as well. We have a truth table for not R and P implies Q or R. So this truth table is going to be significantly larger. There's going to be 8 rows because we have 3 different letters happening here. And we're going to have some columns that we have to include as steps before we get to the final few. So we have P, Q, and R. To get all possible combinations of truth values for that, we need 8 separate rows. When you have 3 different letters, P, Q, and R, P is 4 T's and then 4 F's. Q is 2 T's, 2 F's, 2 T's, 2 F's. R then alternates TF, 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 and TF. In the given logical form, we have a not R. Yes, we have the not R and P in there, but instead of having to think of, okay, what is the truth value not R, and then take the conjunction of that with P, let's make not R its own column for the sake of making things easier. So not R is just going to change the truth value of R here in its corresponding row. So it doesn't take too long to see that the pattern TF, 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 TF becomes FT, 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 FT. Now we're going to figure out the truth columns for each of these pieces individually. I'm going to take the conjunction of not R and P. So I have, after I put arrows on these columns here, just so we know what things we're focusing on, I have a true and a false. That gives me a false. A true and a true gives me true. A true and a false gives me false. A true and a true gives me true. And then note that for these last 4 rows, P is always false, so your conjunction is going to be false. For those last 4 rows. So that is our next column filled in. Now we're going to do a similar kind of thing for Q or R, putting arrows on these 2 columns so we know what we're working with. This is the disjunction. As long as one of them is true, then the disjunction is true. So I have true or true, gives me a true. True or false gives me a true. False or true gives me a true. And false or false gives me a false. Again, true or true, true. True or false gives me a true. False or true gives me a true. And then false or false gives me a false. So there is that final column, that second to last column being filled in. Now we work with the final column. It's this guy here implies that guy there. So false implying a true is a true. That's one of our vacuously true cases. True implying a true is true. False implying a true is true. True implying a false is false. False implying a true is true. False implying a true is true. False implying a true is true. And then false implying a false is true when we are talking about the conditional. So there is our truth table. For this more complicated logical form, P's, Q's, and R's showing up in here now. So again, just as a quick recap, when you're setting up the columns for your truth table, you have a column, the first 2 or first 3 columns, one for each letter that shows up in your given logical form. Then you have a new column for every step to each piece in the overall form, as well as a column for each piece in the form as well. And then your last column is the column for the overall form itself. The number of rows you're going to have is determined by how many letters you have. If you have 1 letter, just P, you're going to have 2 rows. If you have 2 letters, P and Q, you're going to have 4 rows. P goes true, true, false, false. Q goes true, false, true, false. And then third case, if you have P, Q, and R, you're going to have 8 rows. P goes T, 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 F, 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 F. Q goes T, T, F, F, T, T, F, F. And then R goes TF, 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 and TF. So that concludes our video here on truth tables. If you have any questions or comments, please be sure to reach out to me, guys. Email, snail mail, rocks, Braille, Morse code, flare signals, whatever you have to do. Until the next video, take it easy, guys.